All right, this example is based on two things, on Euler formulae and geometric progression formula. So Euler formula, if you remember, that's this is a formula which we call Euler formula. There is what I call the reverse Euler formulae, which express cos and sine like this. It's just a reminder for you what the Euler formulae are. If you have this Euler formulae, if you have this Euler formulae, the main idea which comes from this Euler formulae is this: if I'm looking for this, if I go for this number a, which is the sum of the sines like this, I don't know if you saw this notation. I hope you already saw this notation. It's like an abbreviation for the sum. It means that you take this common term and you add them up by changing the value of this index k from 1 to n. It's just the abbreviation for this longer writing. So Euler formulae essentially give me this. If I want to find this a, I can say that a is just the imaginary part of the sum of the exponentials like this. Because by Euler formula, the imaginary part of this exponential will be sine theta. The imaginary part of this exponential will be sine 2 theta. The imaginary part of this exponential will be sine of n theta. And this one, algebraically, this is just a sum of the geometric progression. Finite sum of the geometric progression. If you think of this exponential ei theta as a number q, then here's the formula for that. Here's the idea which helps me find this sum like this. Now I have to just implement this idea. There will be a few efficiency steps there. I mean, if you try to do it directly, you may stuck with the longer computations, but there are some. Okay, let's just look at this. So my a is effectively, it's a, look at this. If I replace this q here with this exponential, here's the value for a I'm looking for. So I have to compute the imaginary part of this quotient. I'm not going to do it directly. We know how to find the quotients of two complex numbers, but in case of this complex number, it will be rather messy computation. So we will have to do, I will do something else first before I go for the quotient. In fact, if you want to really appreciate the trick I'm going to present in a second, I suggest you do this directly. I bet 9 out of 10 of you won't be able to finish that computation directly. Even though they are finishable, in fact. I mean, it's just, you will give up like midway somewhere. But I gave up, so I have, but you know. Right, so here's the trick. So we're going to compute this quotient. So I will just compute the quotient itself. I just forget about the imaginary part for a while. Look at this. I'm going to factor one of the exponentials from here, from the enumerator. If I do that, no, actually, I'll factor a lot more. Here's the factorization I suggest. Look at this. I took one of the exponentials as a factor in front of the quotient. Then remaining bits in the enumerator, again, I factorize them, and I factorize half of the remaining exponents. And I factorize half of the remaining exponents at the bottom as well. In fact, it's not something which is really far from your intuition, in fact. You probably could guess something like this will be useful because when you look at this bracket, what do you see? Euler formula. Making these exponents one negative of the other, it's a good thing because it just goes to Euler formula straight away. That was the driving idea for this factorization. In fact, this bracket is simply double I sine of this angle. And this bracket, again, double I sine of this angle. So what I conclude now is this. My A is the combination of all of these exponentials. It is here. And the remaining quotient, here it is. Here's the remaining quotient. Like I said again, if you try to compute this quotient directly, you will stuck in the lengthy, messy computations. If you do it via Euler formulae, here's a quotient. This 2i will go in a second, and the rest is just a real number. Now look at this. Remember, we need only the imaginary part of this value, of this quotient, isn't it? This factor, even though it has this factor has I present there, this is like a fictional presence. We'll cancel out it in a second. So basically this factor is just a real number. So if I need the imaginary part of this value, I need to take the imaginary part of this value, which is another instance of a Euler formula, isn't it? Here it is, sine, times this quotient. So the result, in fact, is this. It's an interesting thing, actually. When you take a quotient of two complex numbers that involves this multiplying by complex conjugate, doing that, I haven't done a single time this sort of thing, even though my quotient looks really horrible. It's just the Euler formula does everything for me. It's just that this is a good usage of example of where the Euler formula benefit computations a lot. Well, actually, I opened this, but it has nothing to do with the number a. In fact, this is just a value for this exponential. I didn't realize that, so this is just a value for this exponential. If I need the imaginary part, I take only this piece of this expansion and multiply by this fraction. So the a value is in fact this value.